Hi guys, Tim's back again. I'm going to continue. So this video, rates video number 2. The first video I did was just to talk about an introduction to rates, trying to relate rates to AS, particularly in terms of experimentally how you get rates data and how you get a continuous monitoring of an experiment and how you draw a tangent and work out the gradient to get the rate at any particular time, although initial rate is by far the most common of the experiment, how you get the rate of that experiment experimentally, and that's covered at AS. In fact, I think it's covered at GCSE. This video is taking it much deeper. In fact, this video probably sorts out 70% of the A-level questions you're going to get. 60-70% are in this video. The rest of the videos, we'll be looking at graphs and stuff, are looking at the more difficult aspects of this, which of course is where the real marks lie. But you can get questions like this, straightforward, and there's them. Now, I've put some stuff already on the board, but I just want to, if I swivel that round, I want to show you the sort of objectives that I want to deal with in this particular lesson. First objective is none to do with rates. It's looking at an equation that's on the board and showing the redox for it, okay? Because that's good practice for you. Constantly revisiting things, so wants to do that. Then we've got to deduce the rate equation. We have an equation on the board which is what's called the stoichiometric ratio of particles colliding and reacting, how they react in terms of their molar ratio. It is not the rate equation. It tells you nothing about what influences the rate of that reaction. Totally separate. We were going to deduce the rate equation. K is the rate constant. That is part of the rate equation. Quite often they ask you to calculate the value of K. We will be doing that, and the units of K. But there will be subsequent videos where I revisit it, okay? So bear that in mind. Right, without further ado, let's get right stuck in. I've written an equation on the board, typical A-level equation they use to study rates. Now you might think I've never seen this equation in my life, and you would be wrong, okay? Because first of all, it's an ionic equation. It's only showing the ions that are reacting. The spectator ions don't matter. So get your head around that. What I mean is H plus means there's acid. Hydrochloric acid, nitric acid, and acid gives H plus ions, what are called protons. We'll deal with that anyway later. So an acid is reacted with, now this is bromate, right, where the bromine occupies a positive oxidation state, and that should mean something, because if your halogens join to an oxygen, they can exhibit positive oxidation states. Bromate, you should be able to, now it's got a minus charge in it, so it'll be sodium bromate or potassium bromate in the bottle, but it is only the bromate ions that we're interested in, not the sodium or the potassium. We'll come back to that. But you should be able to deduce the Roman numeral about what the oxidation state of that bromate ion is in that. That is by far the most common oxidation state of all the halogens, the bromide ion, -1, okay? And that is elemental bromine, as you should know, and that is water. Now, if you're on it, that equation should mean something straight away to you. Deduce the redox half equations for that equation for me, please. So pause the video and do that. That, of course, there's a key word, so it is, of course, disproportionation. Deduce the two redox half equations just as an exercise, okay? Obviously, I'll show you what's what. So I'll do that in red now. Bromine here, oxidation state. I keep calling it bromine. Bromate here, oxidation state. 6 minus overall minus 5 plus, okay? 1 minus. Bromine elemental, 0. So, you should be able to construct your redox on the side for that, okay? I'll do it over here. So, bromine 5 plus, okay? Becomes bromine. So, bromine 5 plus 5 electrons, okay? Becomes, right, we've got to watch this. How are we going to represent that? There's 6 of these. 1 does that. Half Br2. That's how you do it. You show it as it actually is, as it actually exists. 1 bromine plus 5 electrons, oxidation state 0. So what you're doing is you're making one elemental bromine. Okay, it's a gain of electrons. So reduction is gain. Okay, reduction. God, blimey, I can't even remember my redox. Look at this. I'm expecting 5 electrons to be lost. Okay, just to nicely match it up. Bromide, right? Br minus. Okay, goes to form elemental bromine. Okay, plus an electron. Okay, but guess what? There's 5 of them. That's handy. 5. Okay, goes to. Now I've got 1 bromine there. I'm supposed to have 6. So 2.5 Br2. That plus that makes the total number of bromines that are produced 2.5 Br2 plus 5 electrons. There you go. Like I say, you don't wait for Tim to show you. You should be able to do those yourself. You shouldn't have a problem with that. Okay, but that's an aside. Now, the next thing I wanted to do with you is, I don't know whether, but I suppose you can see the red, whatever. Let's just look at, so it's a disproportionation reaction. Same unit species, simultaneously oxidised and reduced, all over the place. That is AS and A2. Make sure you know what I'm doing there. Okay, then, so fine, you look at it. Now you're looking for some quantity that can be continuously measured so that at any point you can do the rate for this experiment. You can deduce how fast this experiment is going. Answer, this stuff, bromine is being produced. You will expect the solution to become darker brown as the reaction proceeds. So you can continuously monitor how fast the reaction is going by how darker brown it becomes over time. Okay, so you need a quantity. That might be a gas, it might be mass loss. In this case, it's colour. So you would be able to measure, you'd be able to track that experiment, continuously monitor it. The colour would gradually become more intense over time. And you can, for any combination of reactants and quantities, you can calculate the initial rate by that measurable quantity, the bromine. So that's, I suppose, going backwards. Not going backwards, but that's something that you should by now be able to get your head around. You've got to have a way to measure, to monitor the continual progress and to calculate the initial rate. Okay? Just like I've shown there. Right, now, what are we doing here? We start off with a concentration of that, concentration of that, and concentration of that. We put them all together and we measure the colour using a colorimeter, work out the rate. But what the whole crux of it is this. Here are the starting concentrations in moles per dm cubed of each of the 3 reactants above. Okay, now look, what you're looking for, certainly at this point, they get a bit trickier than this, you're looking for 2 things staying the same and 1 thing changing. Because then you can see how the concentration of one reactant changing influences the rate. And that's how you deduce the rate equation. So, if you look here, we start off, let's look at the experiment is carried out 4 times with different starting concentrations of the reactants. Here is a table of results, and then the rate is taken here. This will be the gradient. Notice these numbers are to the power, they're often, small numbers, so you've got to be a bit careful with your maths, but you shouldn't be worried about those. Right, I look at the first line here. Start off with 0.3 moles per dm cubed H plus, 0.05 bromate, 0.25 bromide. Put them all together, do the experiment, work out the rate. Then I do a second experiment and I keep 2 quantities the same and only change 1. So I've kept my H plus the same, alright? I've doubled my concentration of, so let's put that in there, times 2. That between experiment 1 and 2, just to take 2 experiments and you're looking for 1 quantity changing, that has doubled. That has stayed the same. Okay, now, the examiner will say, use the data in the table to deduce the rate equation. So, this is what you would write when you're answering this. Number one, you tell the examiner which two experiments you're going to look at. So I've just said experiment 1 and 2. They will fit the bill because only one thing has changed. Okay, and then I'm saying to you, right, I've kept, where you write this, you've kept your concentration of H plus constant. That is unaltered. Okay? Come on. Your concentration of bromide, constant. Your concentration of bromate, if you look, I've gone from 0.05 to 1, I've times it by 2. Has that affected the rate? Has that affected the rate of the reaction? Does this bromate concentration affect the rate? Answer, yes it does, because it was 1.68, double the concentration of that, and the rate has doubled. Now that's your very first influence on the rate. That has doubled. 1.68 to 3.36 is times by 2. So I can put a times 2 in there. Now, just helps me to keep track of what's going on. Right, now, basically, so you would then write the rate. So get that constant, that times 2. Rate times 2. Now to put as doubled, times 2. Now that's our very first way, order, what's called the order, right? The rate is times 2. So what would you write, right? You would say, therefore, conclusion. This is what you tell the examiner. Therefore, the rate is, you won't understand this fully yet, first order. This is the way I like to write. With respect to bromate concentration. Right? First order. Now let's just talk about what first order means. First order is, there's 3 different orders. First order is very, very common. Right? First order means basically, if you take a concentration, I'll put this as an aside because it's not part of the actual what you would write in the answer. If you've got a rate of concentration of a substance X and you times it by 2, if it's first order, the rate is twice as fast. If you take the concentration of a substance, in this case the bromate, okay, so that X is just any reactant, okay, and it's 3 times. Maybe you were going from 0.05 to 0.15, the rate would be 3 times faster. In other words, it's what we call a totally proportional relationship if it is first order. You double the concentration of a particular reactant, you double rate. You triple the concentration of a reactant, you triple rate. The concentration of the reactant 0.05 to 0.2, 4 times bigger, the rate would be 4 times. It is what we call a proportional relationship. It is first order. Okay, that is the influence of that reactant on the rate. Yes, it has an influence. Double the concentration, double the rate. End of. Okay, so rate is first order. You'll see loads of these, okay, with respect to that. And I've told the examiner what 2 pieces of data I'm actually comparing. Okay, so number 2, experiment. Let's have a look. I'm looking for 2 lines on here where I only change one. So I've sorted that. I know that's first order. Now look at experiment perhaps 1 and 3. Okay, what's going on here? Experiment 1 and 3, I'm keeping this time, I'm all right for this. I'm keeping my bromate the same. So that's good. So I can put down bromate constant. Okay? 1 and 3, constant. Bromide, concentration. Anything in square brackets means the concentration of the thing in square brackets. Bromide, unchanged, constant. So I'm only changing one thing. What am I changing? From experiment 1 to 3, the concentration of the acid H+. Okay, the H+ concentration goes from 0.3 to 0.6. I'm making it twice concentrated. I'm doubling the concentration of it for experiment 1 to 3. Now, what effect will that have on the rate? 1.68. If it went to 3.36, it would be first order with respect to H+. Doubling the concentration doubles the rate, but it's not. It's going, this is the second order that you need to be aware of. It's called second order. First order, this will be second order. So 1.68, but actually you double that, oh dear, 6.62. In other words, to use a bit of red on here, I've doubled the concentration of that. What's happened to the rate between experiment 1 and 3? Answer, you're going to watch it. 1.68 to 6.72 is 4 times. That's what we call second order. That is a squared relationship. In other words, the concentration of the acid has a, it doesn't, if you double the concentration of the acid, it doesn't double the rate, it makes the rate go 4 times faster. A bigger influence on the reaction, in fact the biggest that we look at A level. So what I can say is, rate, so concentration of that doubled, the rate has gone from 1.68 to 6.72. The rate is 4 times faster. Okay, and then we say, therefore, rate is second order. Right there. Okay, with respect to H+. Okay, we'll bring all this together. Now, just as an aside in red about what second order means, it means it's a squared relationship. It means it has much more influence. In other words, if you've got some reactant, concentration of X, and you double the concentration of that reactant, the rate is going to be 4 times more. If you have a concentration of a reactant, X, and you triple the concentration of the reactant, what do you reckon? 9 times faster the rate will go. Right? If you take the concentration of a reactant and you quadruple it, 4 times more concentrated. If it's second order with respect to that reactant, the rate will be 16 times faster. 4 squared is 16. That's your second order. Okay? There's only 3 orders that you have at A level, and they're all in this question, so you should be fine. Right, next, so this is how you answer. Lots of questions are like this. So then I can go, hopefully, I've got one more to sort. I've dealt with that. I'm looking for another line of the data, the experimental data, where I'm changing this one. This is the only one I haven't deduced the order for yet. Okay, so we took in second order, we took in first order. What's the order for this? I need to look, experiment 1 to 4. 0.3, 0.3, keeping that the same. 0.05, 0.05, keeping that the same. 0.25, 0.5. Right, so in other words, between experiment 1 and 4, that's all right. I've doubled the concentration of that. Get that constant, kept that constant. Okay, we'll come to what happens to the rate for that one in a minute. So, this is what you write in the exam. Tell the examiner I'm comparing experiment 1 and experiment 4. Okay, and obviously I'm answering this in the exam way. I want to be thorough. So I'm saying H plus, concentration, constant. Unchanged, constant. I'm saying bromate, concentration, constant. Right? Right? So, this Br minus bromide concentration, doubling it. Okay? So, how does that affect the rate? What order is it with respect to that reactant, the bromide? Okay, answer, oh, well, I'll double the concentration of this. No effect on the rate. No effect. The concentration of the bromide has no effect on the overall rate. Now, what the concentration is, it doesn't affect how fast. You've got to have it. You've got to have it because it's in the overall equation. It's part of the overall chemistry of the whole equation. This is crucial. If you don't have this, it won't happen. But it won't affect, the concentration of it won't affect the rate. Now that might sound weird, but how does it work or whatever? There must be some pathway where it uses it. We often find, and we'll talk about this later, that if something is what is called zero order, if the concentration of a reactant doesn't affect the overall rate, and we say it's zero order, it's often a substance that's in excess. So there's so much of it, there's loads of it, so actually it doesn't really change concentration as the reaction proceeds. Don't worry about that, but that's sort of what can happen with a zero order. So, basically, rate, in experiment 1 and 4, unchanged, constant, unchanged. Okay? Therefore, rate is zero order. With respect to bromide concentration. There's your answer. There's marks to be had there straight away, no problem. Now that gives us now the rate equation. This is the first one you've seen, but we'll show you some more later. So don't worry about it. So the rate equation I'm going to put at the bottom, and pay attention to this if possible. Maybe I can swing that down a touch, right? Okay, so rate equation. This pulls together, really, in a mathematical expression, how the rate is influenced by the different reactants. So, rate equals, we've got to deduce this rate equation. Now there is a component, I'm going to come back to this, called the rate constant. We'll deal with that later, okay? That is always in there, rate constant. Then you put your reactants in. What's involved in the reactions? Flipping thing turning off. Does my flipping head? Right? I don't know why. Oh, dear. So important. In the middle of something. Rate equals. So you put your reactants involved in this. H plus concentration of. Bromide concentration of bromide. Potentially, the rate is affected by each of those reactants. Okay? Then you put your orders in. First order with respect to H plus. You double the concentration of that, you double the rate. First order. So you can put a 1 in there. The bromate, right? Second order. You double the concentration of that. The reaction is 4 times faster. The rate is 4 times. It's second order 2 there. Third one, the bromide, you double the concentration of that. Experiment 1 and 4. The rate is unchanged. 0 order. That is the rate equation for this reaction. Now, it can be simplified. Rate equals K. We'll come back to this K shortly. First order, H plus, it has an influence on the rate. You can drop the 1 if you want. It's not necessary to put the 1 in there. I must admit I tend to do so. Right? Then this one, the bromate, second order. Okay, that has a massive influence on the rate. It's in the rate equation. Zero order has no influence, and anything to the power of 0 is 1. So if you have a reactant that is 0 order that does not affect the rate, you do not have to put it into the rate expression. Okay, I'm covering a lot in this, guys, so you know. Right, I think I'm going to go for it on this, right? So that's the rate expression, the rate equation, right there, the proper one. Well, both actually, both are perfectly valid. I prefer the top one, to be honest. I think it shows a little bit more detail. Now, I'm really pushing it in this video. I'm covering, many questions. So I'm going to take this out, this here, gone. I'm going to take that out, give myself a bit of space, and I'm going to try and do the next objective, which is calculate the rate constant, K. So we've deduced our rate equation. Okay, so we'll put it back. We'll put it up here. We have deduced from our experimental data the rate is equal to K. H plus concentration has an influence, first order, and bromate, second order. We drop the bromide because it has no effect on the rate at all. There's the rate expression. How do you calculate K, right? K varies, K changes, and the units of K change depending on what the rate equation is, because you have different rate equations for different reactions. So, this is what you take a line of results. Any line you like, and any line you take should come up with the same value of K. So I will take the first line. First of all, I'd like to rearrange things first before I stick. It's a numbers game now, you're number crunching. K equals rate divided by H plus the RO3 minus. Right there. Take a line. Rate. Just do the top line. The rate is, well, like I say, you can take any line you like, and you should get the same value for K. Okay, so try it. If it doesn't, don't ask me. 1.68 times 10 to the minus 5 is the rate. And for that rate, I have 0.3. You see, it's easy to make a mistake on these videos. That's the power of 2. That's the power of 1. I don't need to show that. If you don't do that, you've had it. Right? You've got to put that in there for the rate equation. It's second order with respect to that reactant. It must show a square. So 0.3 times 0.05 round brackets squared K equals. So I'm taking this line here, top line, okay, equals. Now I've hopefully worked this out beforehand like Blue Peter, except it always goes wrong when I do that. Right, so you can work it out, okay, you sort it, right? All good. Got that the right way round. You know what? It's so easy to mess this up. Right, idiot. Right, H plus constant, that's constant, that times by 2, right? That times by 2, rate times by 2, experiment 1 and 2. Okay, rate is first order with respect to that. Okay, I've totally messed this up, right? Keep the 1 and 3, keep the that cross, right? Keep that constant, 1 and 3. Keep that constant, change that. Second, change that, double the concentration of that, no problem. The rate goes up 4 times, so the rate is second order with respect to H plus. Okay, and finally that one, we've changed that, no effect on the rate between that and that, 0 order. So therefore, when I write my rate equation, because I'm an idiot, it's first order with respect to this, second order with respect to H plus. Why I've written it like that, I don't know. So I'm totally the wrong way around here. So that should be there. I do it deliberately to confuse you. It's second order for H plus, first order for bromate. Bromide dropped. So, here, idiot, there. So it's very easy to get mixed up, very easy to mess it around. If you do that, you've had it. So that's the one that's squared. That's the one to the power of 1. So alter that, total nonsense. It's that one squared. Okay? Shove the numbers in. Okay? And, well, I ended up with a bit of luck, let me just check it nicely, 3.73 times 10 to the minus 3. That is the value of K, the rate constant, and that's worth a couple of marks right there. Okay? Idiot. That's right. That is right. Second order with respect to H plus, first order with respect to bromate, zero order with respect to bromide. Okay? Yeah, totally right. Sorry about that. Right, now, K has different units. I'm going to do a whole video on this shortly, right? But I'm going to do it while I'm doing it now because this completes the whole question, all right? Don't worry about this, but every rate constant can have different units. How do you do this? Again, I'll return to this. What you do this. You've got your unit. You just put your unit. You don't put any numbers in. You don't work anything out. You put your units in there. Rate is always moles per dm cubed per second. Don't worry if you can't get this straight off. Moles per dm cubed per second. Those are the units of rate. Divide it by H plus squared. The units of the concentration of H plus are moles per dm cubed. Right? Moles per dm cubed. It's squared. Times moles per dm cubed. It's always like this. When I've done a few, you'll be absolutely fine. Moles dm minus 3. I think the video straight after this just focuses on doing these. So like I say, don't worry. It's like that. Okay? Now, mathematicians should have no problem with this, but you know, it's okay. It doesn't look as bad as what you might think it does, right? So I can cancel, first of all. I can cancel moles per dm cubed on the top, 1 moles per dm cubed on the bottom. Got rid. Okay? Then open up the brackets on the bottom. So now I'm just left with seconds to the minus 1. Open this bracket up, that's moles, squared, this is how you open up a bracket like this, dm to the minus 6. That's the way you do it, alright? So then, nearly there now, that's no good for units. Lift it up, moles, change, when you lift these up, you change the sign, minus 2, dm plus 6, seconds to the minus 1. Those are the units of the rate constant for that particular reaction. Okay, that's how you do it. That's where the marks start to be out. Okay. I reckon 3 or 4 marks for that, 1 mark for the value of K, 1 mark for the units of K. So you've got to be talking 6 marks there to be able to deduce all of that. So a lot, and not actually, once you get into them, first time, yeah, but not actually too bad. Let me just check, make sure everything's absolutely right, and I've made no stupid mistakes, but I haven't. So that, guys, is your first serious rates question. A lot to take on board. But there you go. Thanks for your time. Cheers.